All right, so it's 1:10. I suppose it's time to get started. Thanks for showing up today. If the Wi-Fi is spotty and you drop, I will be posting the recording of this lecture after my last class today, which will be at 4. It takes in very short order. I should have this up, so it'll be up no later than about 6 this evening. I would like to make the announcement that I managed to get to CVS really early this morning and get a rapid test, and which came back negative. So even though I'm feeling a little under the weather, I suppose it's just a nasty cold instead of COVID. So I'll be running the class in person starting Thursday. So we won't necessarily have this type of Zoom structure. I'm looking into recording the what it's going to take to record the in-class lectures. For sure, I'm going to continue posting the supplemental Zooms that are the supplemental videos that if you looked at the webpage today, I put one up. So there'll be 20 to 30-minute videos in support of every lecture. There's not going to be a quiz this week because there's actually a lot of people moving in and out of the class with adds and drops. So we'll do the first quiz next week on Friday. Whoever's pumping music at me might consider muting. Thank you. And then the last thing that I want to talk about, just give the opportunity to be talked about before we kick off the math today, is we have the workshop facilitator for this course here. This is Andrew. I would encourage you to participate in the workshop if you've never done it before. It's a nice way to supplement the activity in the class. I was a facilitator myself when I was a student here. So I'll let Andrew introduce this, and let me highlight you.
Thank you. Hi, everyone. My name's Andrew. I'm a 4th-year electrical engineering major here, and I'm going to be your math workshop facilitator this quarter. For those of you who may have not heard of workshops before, it's basically a 1-unit supplemental course that gives you an extra learning environment to really hone in on the difficult subject material in this class. We meet twice a week on Monday and Wednesday from 6 p.m. to 7:30 p.m. And so in those sessions, I prepare lessons to go over some of the difficult class material that we did is up to date with the lectures. I attend all of your lectures with you. So everything that we do will be in time with the lectures and with things that I might look at and go, oh, that looked a little difficult. People looked a little confused. I definitely want to make sure we focus on that next time. A lot of people say that this is one of the most difficult calc classes that you'll take. So I think that this is a very valuable workshop for this class. I've done this workshop before for Calc 3 4 times before, or I guess this is my 4th time doing it. So I've had a lot of time working with this material and teaching students. And so time and time again, workshops have shown that it really helps students grasp the material more in depth than just studying independently. So if you would like to sign up for these and attend, I'm going to post a little bit of information in the Zoom chat. Okay, there we go. So what I just posted, it has my email, it has the meeting times, Monday, Wednesday. It has the meeting location. We're meeting in person in the Math and Science building. We're kind of down on the 1st floor of it, down the hallway a little bit. And then there's a class number there as well, which you can use to add the class. So unlike maybe tutoring things that you just show up for, this is an actual class where you are required to show up to it every time, and basically you get a grade for it. And the grade is only based on being there. So you're not responsible for any extra homework or anything. It's just a show up, practice material, and if you're doing that and you're participating, then you get credit for the class. So are there any questions about this? Anyone? Okay, feel free to shoot me an email if you have any additional questions. Our first meeting is going to be Monday, so tomorrow. We're going to be meeting at 6 p.m. tomorrow at that classroom. So if you're interested, please show up and I'll give you more information about what it's going to be like and how to sign up for the class.
Do you mean tomorrow or do you mean next week on Monday? You said Monday.
Oh, did I say Monday?
Yeah.
My apologies. Okay. Wednesday. So as in tomorrow, we're going to be meeting Wednesday.
Cool. Thank you.
Right. Yeah, thank you.
All right, so I will actually encourage you again. These are excellent opportunities to grapple with the material in an environment of other people who are doing it. They're very well thought out typically, and it's just fun to do math with other people, especially since we've spent the last year and a half or 2 years or however long it's been now, like as little cells, attached to each other through cameras. So they're fun, they're useful. This class is got a reputation of being difficult. So if you feel like you need that, you should participate. All right. So let's move on. So I'm going to actually open the floor briefly for any questions before I move on with today's mathematics. Are there any questions from me that I can answer before we get started? All right. So let's do it. So today we're going to be talking about the first part, at least, of section 11.2, which is about infinite series. And the motivation for infinite series comes from looking at expansions of rational numbers. Actually is maybe the first place where you see why you'd want to do this. So the upshot here, hold on, I got to pull my notes open, is that when you start looking at things like infinite decimal expansions, right? So even a number like this, which, so 0.11111, there's a number that's it's pretty easy to say what that means in terms of places, right? I mean, when we write this, we mean the number 1/10 plus 1/100th plus 1/1000th plus 1/10,000. So finite decimal expansion is pretty easy to write down a list of numbers that represents it. I mean, that's what a decimal expansion is. It's a sum of things. One thing that we end up with when you start looking at rational numbers, and a lot of times we sort of learn this without taking time to think about how weird this idea is we think about infinite expansions, whether irrational numbers where they're infinite and don't repeat, or rational numbers where they're infinite and they do. So this is a non-terminating but repeating decimal pattern. And if I wanted to write this down in terms of what I mean by its places, I would have to start by putting the 1/10th for the 10th place, and then there's another 1 in the 100th place, and another 1 in the 1000th place, and you just keep going, right? The 10,000th place, the 100,000th place. But in order to write down what this number would be, in order for this thing to actually have a decimal expansion, I would have to do this forever. I would have to keep adding. And so that is the sort of thing that intuitively we can think about what that would mean. But as soon as infinity gets involved in this type of math, you have to be careful, because how do I even know that it's a meaningful thing to add an infinite list of numbers? There's a process where I could say, oh, well, just do it forever. Like, how do I know it adds up to something? How do I know that this idea can be used in this context or other contexts? So this is the basic idea of what we mean by an infinite series. You can think about it as being an infinite sum. And the big questions about infinite series and infinite sums is, when do they add up to a number? Right? That's the first intuitive question, is when I have an infinite list and I add it all together, when does it actually add up to something? But there's a more basic question, is what does it even mean to add up? What does it mean to add up an infinite list? Okay. So let's be a little bit more formal about what we mean by an infinite series. So you start with a sequence. And the sequence you can think about as being A1, A2, A3, and so on. So an infinite list of numbers. Okay. Alternatively, just to remind you, we could use this notation, which really, I think, emphasizes the fact that this is an infinite list. Then if we add it up, as soon as we take a sequence and we connect it together with addition, this thing is an infinite series. Okay, so it's an added infinite sequence. And it's typical that if we have a formula for the terms of the sequence, that we can use what's called sigma notation, which I'm presuming that almost everyone in here has seen before, where this thing can also be written A1 plus A2 plus A3 and so on, could be written as the sum from n is equal to 1 to infinity of an. Now, I want you to be a little cautious about this because this is the same kind of, we're hiding details when we write this. This is an object that I say, oh, it exists. You just start at 1 and you go forever. But this is what's called a formal object. It hides a meaning that we're not seeing. Like secretly in the background here, this thing is either not defined or it's a limit. In the same way that when we studied integrals in calculus 2, whenever I have an integral with an infinity in it, was really secretly a limit. These are going to turn out to secretly be limits as well. And that's the approach that we're going to use to make this a meaningful object. Okay. So how do we think about these things as adding up? Like, say you get away from rational numbers. What would I mean if I say an infinite series can add up? Well, let's just consider the sequence: 1/2, 1/4, 1/8, 1/16, and so on. I'm going to assert that we should intuitively think that this adds to something when I turn it from a sequence into a series. So this is a sequence of terms. As a series, it looks like 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. This is a series. What number does it add to? What number should it add to? So I'll give you a hint here. Or actually, does anybody have an answer? Graphically, we're doing this. So you start at 0, and then you add a half to it, and then you add a quarter to that, which gets you here. And then you add like an eighth to that, which gets you here, and you add a 16th to that, which gets you here. What number sits out here that you're getting close to as you continue adding? It is 1. So Lucas says it's 1. Okay. Why should it be 1? How did we do that? Intuitively, how are we doing that? I'm assuming none of you guys are sitting down with a formal definition of an epsilon delta limit and computing this. So why should it be 1?
Because you're always adding something half of what you just added, so you'll never actually get to 1.
Okay, that's true, but how do I know I get to? So you're right, I can never get to 1, but how do I know that 1 is the thing that it's getting close to? Why not 3/4? Why not 999 1/1000ths? How do I know it's 1 that this adds up to? Because if it's going to add up to something, it better be a unique number.
When you add only half of the next one, you're only getting halfway there. So
okay,
every single step is halfway to the end.
Okay, so that is correct. And I'm actually going to say that still doesn't tell you that is an argument for the convergence. The fact that you're adding half of the number that you're going each time says, okay, it must be going somewhere, because if you're only going half, you can't get further than some point. But why 1? What's 1/2 plus a quarter?
3/4.
Okay, so there's 1/2, there's 1/4, there's 1/8, there's 1/16, there's 1/32. So this list right here, this is the terms, right? That's the sequence. Now I'm going to start adding the terms of the sequence. I'm going to define another sequence called Sn. This is the thing that I'm after here. So intuitively, when people think that this is equal to 1, this is what they're doing. 1/2 plus itself is a half. Now add a quarter to that, and what do you get? 3/4. If you add an eighth to that, what do you get?
7/8.
Okay. And 15/16 and 31/32. The idea here is that this is the sum. These are called the partial sums, which we're going to define on the next slide. But the idea here is that intuitively what you're doing when you think of an infinite series, and it's an easy enough series to grasp, you're taking a number and adding it to the next number and seeing what that is, and then adding the next number and seeing what that is. And really what you're doing is tracking, okay, this thing that I'm building in finite steps, does it have a limit? Is there an obvious limit that falls out here? And what you're doing intuitively is you're thinking, okay, these numbers sure look like they're approaching 1. 31/32, 63/64, 127/128. Those numbers are getting closer and closer and closer to 1. Okay. So The way that we really talk about the convergence or the adding up of an infinite series is we don't actually think of the infinite series as an object. We think of it as being related to a finite list of things that are added together. So the nth partial sum of an infinite series maybe I should change index here so I'm clear. So let's make this series run from k equals 1 to infinity of ak. The nth partial sum is Sn. So we use S, the little Sn to mean the nth partial sum. And it's just start adding at A1 and finish adding at An. So it's the sum of the first n terms. And so in the previous question, we saw that Sn sure looked like it had the form 2 to the n minus 1 over 2 to the n, right? We're not going to prove that right now. We'll do exercises later. But in our previous exercise, the nth partial sum for the series 1/2 to the n looks like 2 to the n minus 1 over 2 to the n. And the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n is 1. So we're going to talk about, formally, we're going to say that a series converges when its sequence of partial sums has a limit. That's the definition of the convergence of an infinite series. So we studied sequences first because we're going to use sequences to study series. Again, remember, if I'm going too fast or you guys need to interject, it'll be much easier in the classroom on Thursday because you can just sit there and look confused or raise your hand. But it's hard for me because the way I've got this set up, I can only see 4 faces at a time. All right, so formally then, we say that an infinite series converges if the associated sequence now of partial sums has a finite limit. I'm trying to not use the word converge twice because I'm trying to focus the idea of that what we're studying here is convergence of the series, not the sequence. So if the sequence of partial sums has a limit, then that limit is finite, then the infinite series converges. Okay. And a lot of the work that goes into a class like this is studying, okay, well, what can we say about sequences of partial sums? When do they exist? Okay. If a sequence does not converge, then it diverges. So I should say if a series does not converge, then it diverges. And there's a lot of ways that a series can fail to add up, right? So again, intuitively, you're thinking when a series converges, you're thinking that as you continue adding terms, somehow that the total pile of all those things approaches some number. So at a very basic level, when we first start introducing series, essentially we're going to be working directly often with the sequence of partial sums. And a lot of the techniques that we're going to develop that involve when a series converges or diverges are going to involve looking at the sequence of partial sums. So this is the main concern of this part of the course is when does an infinite series converge or diverge? And the most basic tool we have is Sn, the sequence of partial sums. So as an example where this is basically a not a lot of work example. Suppose that somebody comes along and tells you that you have an infinite series, and somebody else did the hard work for you. So suppose that this is an infinite series. And somebody computes Sn is equal to 2n plus 3 over 3n. Somebody does the work for you. Boom, there's the sequence of partial sums. What they're saying here when they say this is that a1 plus a2 up to an, if you add the first n terms, you get 2n plus 3 over 3n. So like, for example, if I start at a1 and I add up to a10, then it's 2 times 10 plus 3 over 3 times 10, which is 23 over 30. It's a formula that computes for you, given us the number of terms, what the sum of those first number of terms is. Okay. Normally, you actually have to do the work of finding the formula, but this is an introductory example. What does the sum from n equals 1 to infinity of an converge to, if it does? So you just take the limit. A series converges if the limit of the sequence of partial sums exists. So you take the limit as n goes to infinity of the sequence of partial sums, which is the limit as n goes to infinity, in this case, of 2n plus 3 over 3n, which is 2/3 by techniques that you would have picked up in your limit chapter, right? So for example, last time we talked about dividing top and bottom of a rational expression by the largest power of n. You could use L'Hopital's rule on this if you like, but the idea is that in many cases, we're going to be doing these very simple limit estimations of these sequences, okay? Now, this is a very easy example of this question because normally this is where the hard work is. So hard work goes into finding the partial sums for a particular series. But if somebody just comes along and gives you the sequence of partial sums, it's really easy to work on a question. Okay. All right. So how do you do it if you don't have the formula given to you? So we can look at the example that we had before. So before we had 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and so on. If we don't actually know Sn and we have to compute it by hand, we can do that just by like formally writing down the list of partial sums. S1 is the sum of the first term of the series. S2 is the sum of the first 2 terms of the series, 1/2 plus 1/4, which in this case is 3/4. S3 is the sum of the first 3 terms, which is 7/8. S4 is the sum of the first 4 terms, which is 15/16. And you might wonder why we spent the time in the sequence section talking about finding the formula for the nth term of a sequence. This is one of the first applications of that idea. So when I'm looking at this sequence and I think, well, this is the n equals 1 term, and this is the n equals 2 term, and this is n is 3, and this is n is 4, can I find a pattern for Sn? I notice the denominators of these things are powers of 2. In fact, 16 is 2 to the 4th, 8 is 2 to the 3rd. It looks like 2 to the n is in the bottom of the fraction. And whatever's in the numerator is 1 less than that. So that right there is a formula for the nth partial sum. And if you want to know what the sequence, or sorry, the series converges to, you can compute the limit of Sn, which is the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. Again, there's a couple of different approaches to this. The easiest way in this case is actually to divide the top and bottom by 2 to the n. And what you'll end up with here is that this limit is 1. And since this limit is 1, this sequence was also, or the series added up to 1. This is a much more typical example of the way these exercises go. You get a formula, if it's not one that you know how to work with, you might compute a sequence of partial sums, and then you compute the limit of that once you have a formula. Okay, so this is kind of a busy slide here. Any questions? I imagine for like a lot of people, this is review. This is going to get kind of gnarly in just a couple of sections. So make sure that you're taking the time, even if you've seen this before, to review these questions diligently. All right, so what is the single most important series that exists? Or a family of series that exists? You would have learned this perhaps for the first time way back, maybe in Algebra 2 even, when you studied geometric series. Okay, and a geometric series is a series that has a special form. So the way that you get the next term in a geometric series from the previous term is by multiplying. So this is what a geometric series looks like. And in order to make the formula nice, we're going to think of this as being a times r to the n minus 1. So we're starting the index list at 1, and the r starts the n minus 1 power. And the structural feature of a geometric series is that I get from one term to the next by multiplying by r. And I multiply by r again, and I multiply by r again. These come up in nature and science frequently because they represent an iterative process where each time you're like multiplying by the same number over and over and over again, the process of adding. Now, the reason that these things are so important, as many ideas in math turn out to be, is that they were invented in a time before computers, and you can actually write down what these add up to. There's a formula for this. And many of you may actually remember this somewhere tattooed in your brain cells. So I'm going to give you a second to think about it. And if anybody has not actually looked at this, it doesn't have the book open, and I have to trust you on this. Does anybody know off the top of their head the formula for this? I'd be impressed. All right. So even if you don't want to say, you might write down on your page what you think it is, and then I'm going to write it down here. So if certain restrictions apply to the ratio, the r value that we're writing here, this adds up to a over 1 minus r. So this is the geometric series formula. Does anybody, okay, so maybe that rings a bell. Does anybody know the condition on r? Because I'm going to talk about that next. Think it to yourself if you don't know. All right. So actually, if you guys have been talking and I haven't heard you, it's because I have like somehow slipped my headphone out of the headphone jack out of the headphones. Yes, almost less than 1, but -10 is less than 1. So if I just keep multiplying repeatedly by -10, what's going to happen is I'm adding and subtracting terms that are going -10 plus 100, minus 1,000, plus 10,000, minus 100,000, which means as I keep adding, it's going to flop left and right, but with numbers that are getting progressively larger. So it's not just less than 1. It also has to be greater than 1. So this is true for, you can think about it as the absolute value of r is less than 1, or you can think about it like this. And the reason is, if you think about the behavior, of r to the n, r to the n tends to infinity if r is bigger than 1. And if you think about what's happening, if we have a list of numbers and we're adding more and more numbers to the end, and we want that to settle down on some limit, if I have numbers that are exploding away to infinity and I keep adding them over and over again, there's no way that sum can ever converge, right? It's never going to add up to something if I'm adding larger and larger and larger numbers. And it's even worse in some sense if I have numbers that are smaller than -1, because then there's no limit at all. R to the n goes to infinity and minus infinity at the same time because it flops back and forth. But if r is between -1 and 1, then r to the n goes to 0. Right? Fractions, this is a thing that should be encoded in your brain. Things that are less than 1, and between -1 and 1, when you take their powers, they get small, right? They go to nothing. Now there's a derivation of this, which I think is really cute. I'm not going to talk about it in here, but you should read that in the text. The derivation of this formula, it requires nothing more than a clever insight and a factoring formula that you would have picked up some point in the past. So how do geometric series come up in practice? Well, the first thing, first off, let's make this formal. So this is a theorem, actually, that the sum from n equals 1 to infinity of a r to the n minus 1 converges to a over 1 minus r if the absolute value of r is less than 1. Otherwise, it diverges. I should be a little bit careful here because we're implicitly assuming here that a is not 0, because a list of zeros adds up to 0. So that's kind of boring. So another approach to our question from before, 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. Another approach to this would be to recognize that this is actually a geometric series where each time I'm multiplying by 1/2. And since I multiply by 1/2 at each term, that means r must be 1/2. That's the ratio that gets me from one term to the next. And the a value for a geometric series is just whatever's in slot 1. So a is also 1/2. Now, the absolute value of 1/2 is definitely less than 1. So this will converge. And what does it converge to? A over 1 minus r, which is 1/2, over 1 minus 1/2, which is the horribly uninteresting answer, 1/2 divided by 1/2, which is 1. Okay, so this is a way of attacking these types of geometric series that does not require having to resort to the sequence of partial sums. So generally, when you're looking at a series in this class, it's going to be highly, especially in this, like, you know, if you don't know what type of series it is, and we've got 8 different tests we can use to figure out if it converges, always check first to see if what you're looking at is a geometric series. So I'm going to give you one that's slightly more challenging than this. This is an example 2. Again, when you see an unfamiliar series, first thing you should check is it geometric? And that just means you need to figure out what the ratio would be if it is. What number do you multiply to get from 5 to minus 10/3? Well, this move right here would be done with minus 2/3. And this step, is that also by minus 2/3? Well, minus 10 times minus 2 is 20. And 3 times 3 is 9. So this is also multiplication by minus 2/3. And occasionally, I'm not one of them, but you might get a professor who's mean and gives you another step that maybe the first 2 look geometric, but then something else happens. So this right here is also by minus 2/3. And so generally the assertion I'm going to make is if a pattern holds until I hit the ellipses, you can assume that it continues to hold. So I assert this is geometric. And again, we've identified the ratio. All I need to do for a is pick out what the first number is. And so the absolute value of minus 2/3 is less than 1. So it converges. And it converges to 5 over 1 minus 2/3, which is, what do you end up with here? 5/3 plus, oh, that's my bad. 1 minus r. So in class, somebody would have yelled at me about doing this. 1 minus minus 2/3, which is 5 over 5/3, which is 3. Right. These are kind of the easy mode version of geometric series, right? But you should always check first. A slightly more complicated example that you might have with geometric series looks like this. So I could ask the question, does the sum of 2 to the 2n, 3 to the n minus, or sorry, 1 minus n, converge? If so, to what? So again, we don't have any tools. We have two things we could possibly do with this series at this point. We could write out the list of what the terms look like, or we could try to put it in the form of a compute partial sums. So we could compute partial sums, or we could try to put this in the form of a geometric series. So the form of a geometric series, if it is geometric, I should be able to put it in the form, the sum from n equals 1 to infinity of a times r to the n minus 1. I should be able to manipulate that. And you can do that directly from the list of terms, but I'm going to show you how to do it without having to take. So in this particular example, what I'm going to do is I'm going to leave the sigma notation alone, and I'm going to algebraically manipulate the terms without actually writing it out term by term. Now, you're allowed to do this term by term. It's okay to do that. Okay. But if you were going to try to manipulate this into this form, the first thing you need to do is collect everything to the nth power kind of by itself. I mean, there's something to the nth power here. So the first manipulation we could do is we can make sure all the powers are n's. So 2 to the second to the n. There's this 3 to the first. I'm going to pop that off. Remember, the power rule says 3 to the first, 3 to the 1 minus n is 3 to the first times 3 to the minus n. And that's the same as the sum from n equals 1 to infinity of, okay, so we get 4/3 to the n times 3. 3 to the minus n, that's 1/3. That's where the 1/3 down here came from. 2 squared is 4. Anything to the nth power, I can kind of squeeze together and pull the power out. So this move right here was done so that I can get something that looks like a ratio. This still is not quite in the right form because there's an n here. And in our formula here, there's an n minus 1. So I actually have to pull one of those 4/3 out of the structure to get this in the right form. So we end up with the sum from n equals 1 to infinity of 3 times 4/3 times 4/3 to the n minus 1. So I just pulled one of the 4/3 out to drop the power because I need the form to be exactly the same as the geometric series form in order to use the geometric series formula. So we end up with, in proper geometric form, 4 times 4/3 to the n minus 1. Now, at this point in the manipulation, you would say it diverges because r is greater than 1 and it's geometric. And there's nothing else to say. Since r is 4/3, r is greater than 1, geometric series with r greater than 1 diverges. Okay. But this type of approach that we've done here, where we're looking at the formal sum and we're manipulating it algebraically within the sigma notation instead of expanding into terms, this is probably a more typical kind of or high level approach to some of the things that we're going to be doing later. And you need to get comfortable with the idea of manipulating the sigma notation directly. Okay. I'm going to do, the next thing I'll do is I'll write out, like, if you got stuck and you want to try this term by term, the other way you could do it, 2 to the 2n, 3 to the 1 minus n, you could just write some terms down. The n equals 1 term is 4, it's 2 to the second times 3 to the 0, which is 4. The n equals 2 term is 2 to the 4th times 3 to the 1st minus 1st, which is 16 over 3. The n equals 3 term is 2 to the 6th times 3 to the minus 2. 64 over 9. So this series is really 4 plus 16/3 plus 64/9 and so on. And you could recognize here that you're getting from one term to the next by multiplying by 4/3. And since r is equal to 4/3, the absolute value of r is greater than 1, this diverges. Now, probably a lot of you are looking at that and saying, this is so much easier than doing it the other way, right? To just write some terms down, identify what the ratio is, and do it this way. It is easier to do this when you have geometric series for sure. But I'm trying to also encourage you that if you're given something in this sort of algebraic form like this, try to manipulate it algebraically, keeping it in sigma notation, because that's a skill that's going to serve you well as we go on in the chapter. Okay. But there's nothing wrong with doing what we did here. This is a really elegant way of analyzing this problem, is actually to be able to compute the series that the formula represents. Okay. Right. So I like to try to keep these classes. I mean, so I've talked about math for about 40 minutes. And normally, so I'm probably going to stop here because there's a natural segue into the second part of this section. So that's what we're going to talk about on Thursday, is the second part of 11.2. We could do more here, but in a given classroom lecture, nobody, I mean, at least no lecture I'm in, I talk for 50 minutes in a row, right? So I'm going to sum up what we did here today. I'm going to post this, and I want you guys to get started on this part. And on you've got more than enough information here to start on the first part of the homework from 11.2. What we've talked about today is, so in part 1, we'll open the floor for questions after I sum up here. So we talked about the definition of an infinite series. And really, you should think about an infinite series in some sense as a limit of partial sums. And then we talked about the geometric series. And in particular, we looked at a couple of different examples of lists. And we looked at a formula example in sigma notation. So next time, what we're going to talk about, I think, are some really fascinating types of series, which are called telescoping, where you compute partial sums and then the middle terms all cancel out algebraically, which is going to involve some higher level algebraic techniques like partial fractions, which is why I don't want to just throw it on in the end of a lecture here. Okay. Are there any questions about anything I did here I can answer before I let you guys go for the afternoon? I mean, we won't end early when we're in person, because there'll be questions and things I can do with you. Like I will never run out of things to talk about, and I can always ask you questions to work on if I'd like to. Is there anything I can answer here in this lecture before we go on? All right, then I have a challenge for you. Here's my challenge question. So now, if you believe the definition that this is not much of a challenge, but if you believe the definition that we just wrote down, you can solve one of the oldest, angriest questions on the internet, which is 1 equal to 0.99999 forever? Right? That gets posted. Oh yeah, no, the answer is yes, but can you prove it using the techniques that we just that we did in here? And the clue is, or the hint is, you can think about that as an infinite series and then find out what it converges to. And then you can be the pedantic math student that rolls into some, group of people yelling at each other about this question and assert confidently that if you believe the definition of infinite series, then the answer is clearly yes. All right. So I'm going to be in here for the next 5 minutes. You guys are welcome to go. I will post this. I'm going to stop recording. You're welcome to hang out if you've got questions for me. And otherwise, I look forward to seeing you in person on Thursday. So thanks for your attention.